Hello, everyone. My name is Aroho Prisla, and I'll be taking us through the semi-supervised tree-based architecture for predicting anti-malaria failure in HIV co-infected patients, compiled by Group SWML13. So the contents of our presentation are the introduction, related work, problem statement, research questions and objectives, research contributions, system methodology and architecture, the dataset description, model selection and deployment, results, model compression, conclusions, plus the next steps. So we are looking at how HIV malaria co-infection is a serious burden in rural areas like Uganda. When HIV suppresses immunity, patients face higher parasite density and a greater risk that anti-malaria drugs will stop working. So the challenge for machine learning is that the clinical datasets in resource-limited settings have very few labeled records, which is about 75% of our data that has no confirmed WHO clinical stage. So the standard deep learning models overfit these small datasets and offer little clinical interpretability, while tree-based ensembles handle nonlinear biomarker relationships well and explain their predictions clearly for both, which are both essential for a clinical triage tool, meaning that our tree-based ensembles better handle nonlinear biomarker relationships because for them they can handle labeled and unlabeled data, which is widely the data that we are using. So our problem statement is while the clinical utility of predicting treatment failure is clear, the underlying machine learning bottleneck lies in several label sparsity and the mathematical risk of manifold distortion during imputation. This simply means that the core technical problem is label sparsity combined with manifold distortion risk, with 75% of labels missing. Naive imputation methods like filling missing values with the global median artificially collapse the variance of the feature space. And when you try to propagate pseudo labels across that flattened space, the model systematically misclassifies high-risk minority patients as average. And this isn't just a performance issue, it's a patient safety issue. And our solution was to apply the multivariate iterative imputation via Miss Forest before any manifold projection, preserving the true physiological distribution of the biomarkers. And then our research questions and objectives. We have 4 core objectives, and the first one is to quantify the relationship between CD4 count and treatment failure risk, and secondly, to identify which ACT drugs remain most effective across different HIV immune tiers. Thirdly, to map the geographical regions where HIV prevalence and anti-malaria drug resistance overlap most dangerously. And fourth, to determine whether immunocompromised patients need accelerated escalation to second-line treatments. Like we find out which treatment is not working for these HIV patients so that we can switch their treatment quickly before damage is done. And then our research contributions and outputs, we developed the predictive failure risk that integrates the current CD4 count regional resistance markers to quantify how specific immune tiers directly correlate to malaria treatment failure. We also built a drug effectiveness mapping tool that identifies the ACT treatment with highest clearance rates in the presence of HIV-related immunosuppression. And we also mapped the high-risk overlap zones by linking the regional HIV prevalence with localized data and sulfadoxine, pyrimethamine, and piperaquine resistance to specify which clinicians face the highest problems. And we also proposed a system to help HIV positive patients get the right medicine faster. That is to achieve our research questions and objectives. Moving on to our methodology and system architecture, as illustrated in this diagram here. Our architecture uses a ground truth only test split of 30% of labeled records, and these were held back strictly for evaluation, and the remaining labeled data plus all the unlabeled records were fed into semi-supervised training, and we moved on to evaluate 12 models, which include some of them are the label propagation, self-training XGBoost, label spreading, self-training with Gaussian process classifier, the Gaussian process regression, XG boosting plus sharp values, co-training, tri-training, Bayesian hierarchical TVSM, and the Laplacian regularized least squares, plus the elastic net architecture training and audit. And all these are covered in our methodology and system architecture, where we had to choose the self-training with Gaussian process classifier that gives us this architecture. And also, we look at our output results for the 12 models. While looking at these results, we will see that self-training with Gaussian process classifier gave us the highest accuracy and F1 score. And while we move on, we see that we have the ROC area under curve for some of these models, label propagation and self-training. And then after selecting our model, we will have, since we chose the self-training with Gaussian process classifier with an accuracy of 0.9412, which is the highest, and supports semi-supervised learning, which learns from both labeled and unlabeled data, which is ideal since our dataset has incomplete labels. Our F1 score is 0.912. We did an explainable AI audit with sharp and permutation importance for this model. And this is its architecture, where we have raw clinical data, the pre-processing service, a 12 model experimental group, self-training, GPC was selected. We did an XI audit, then we deployed with the Streamlit app. We got our confidence gate and the evaluation metrics. So this is our selected model architecture, the architecture for a Gaussian process classifier. We have our raw data set. It is put through feature scaling to normalize our data. Then we train our best classifier, in this case, which is the Gaussian process classifier. Then we predict the unlabeled samples first. We select the high confidence predictions, add pseudo labels, retrain the model iteratively, then to the final predictions. So we compare our self-training with Gaussian process classifier to one of the best models that we had that would have come close, which is the label spreading. Label spreading, in comparison to self-training, has 0.934641 accuracy, a precision of 0.91, recall of 0.93, and an F1 score of 0.918. This is the interface of our selected model, our deployed model. So it has three parts, which is the single prediction, and then the batch prediction and the model evaluation. With the single prediction, given that we have very many records, it might be so difficult to use because you have to manually type in these values, and we go up to almost 761 records, which might be difficult. That means we can opt to use the batch prediction. And with the batch prediction, you just need to enter, you will drag and drop your file of the dataset with the corresponding columns. And then you will run batch prediction, where you will be given the metrics after running the prediction. Then even in the model evaluation, where we want to evaluate our model, you will enter the batch, you will drag and drop the data set with the information that corresponds to the columns, and you will be given the metrics as seen here. So to demonstrate our developed product that we developed using that we deployed on Streamlit, the Streamlit web application predicts HIV malaria therapeutic efficacy. It classifies the cases as active, which is 1, or not active, which is 0, using a self-training GPC and trained on the combined clinical data. So the workflow would be the user will open the URL provided after running our code that is in app.py in the IDE. It opens the Streamlit app in the browser, and the app has 3 tabs, as we have explained. And then the assets, our IP assets would be a trained self-training with Gaussian process classifier model. In this case, our file is named self-training gpc.joblib, our model. Then a standard scalar, capturing trained data distribution scalar.joblib. And then an ordered featured schema that ensures column alignment to prevent shape mismatches, which is feature columns.joblib. Lack of the feature columns.joblib would mean that most of our columns are not going to align. You'll find that while you're entering the data in the deployed model, entering it in a wrong in the wrong place would give us an error. So that means that it is very important to have the feature columns.joblib model. Then we also have the Streamlit clinical interface with 3 tabs, which we get after running app.py in the IDE as seen previously. Then we go to model compression. So with model compression, we had our base model, which we had deployed before, which is the self-training with Gaussian process classifier, which is, in this case, we call it our teacher model. So the accuracy of it, as seen before, is 0.9412. F1 score is 0.9127. Its model size is 3,194.45 kilobytes, and its training time is 0.0 seconds. Then our knowledge distillation. So the large teacher model trains a smaller student model. In this case, our large teacher model is the self-training with GPC. So this gives us an accuracy and F1 score similar to our teacher model. And the model size is 1.2 kilobytes, that is a bit smaller than what we had seen earlier. Its training time is 0.137 seconds. And the reduction is giving an 100% reduction, a size reduction versus the teacher reduction. Then we move to pruning. Pruning removes the less important features or the parts of the model that are not required, and still gives us the same accuracy and the same F1 score as our teacher model, the self-training with Gaussian process classifier, but gives us like the model size is not so small compared to knowledge distillation. The training time is 3.286 seconds. Takes a very short time to train, and the size reduction is only 3.4%. And then quantization converts the model weights from float 64 to float 32. The accuracy and F1 score here are the same all through, from self-training to knowledge distillation to pruning, even to quantization. The model size is also not, it doesn't give us a big drop, just like pruning. And the training time is 0.08 seconds with a negative 0.0% reduction compared to the teacher model, which is self-training with GPC. So these are the visualizations, and you can see that it simply gives us it visually shows us the comparison of the previous slides comparing the model size, the performance, and the training time of each of the model compression techniques. So, in conclusion, the fundamental limitation of this architecture is the reliance on its initial distribution of the 25% ground truth labeled cohort. And we reaffirmed the anti-malaria failure prediction from a naive statistical problem into a disciplined semi-supervised classification task with explicit safeguards against manifold distortion and pseudo-label bias. And the main limitation is a reliance on like we've said, on the initial 25% labeled cohort. If that subset carries demographic or socioeconomic sampling bias, the pseudo-label propagation phase can amplify it to support reproducibility and external clinical audit, and we will open source all imputation scripts, calibration thresholds, and evaluation splits with fixed random seeds. In this case, this deployed model can actually be used in places with a limited internet service. It can actually be used remotely. And then we move forward to the next steps. The next steps show that we plan to validate against the recent 2021-2024 global resistance datasets and integrate genomic resistance markers for PPQ and SDX resistance, and expand the semi-supervised pipeline to leverage even larger pools of unlabeled clinical data. We recommend that public health bodies prioritize the patients in moderate and severe immune tiers, and that these model findings be integrated into national treatment guidelines. Thank you.